Just this two. Those who use this for reference, does the recording come okay? The zooming, everything?
It's okay.
Yeah.
Some of the writing is not clear, but
It's not clear.
But we have already notes with us, that's why it's okay. Some of the last time I found us in one video, I cannot.
Is it because we are not zooming it sufficiently?
I think that became.
How can we fix it?
That became a blur at that time. It will be.
So how do we fix it?
I can be there if it is going very, if we made it full screen, then we will see when we are recording, right? If we cannot see there, then the video will be bad.
Yes, so my question
This
is,
is minimized window, so we can see some.
oh, make it full screen.
Full
Ah,
screen.
okay,
So
okay.
then we will see on the day if it is going.
Okay,
bad.
okay. Got it. I'll do that. Simulates it. So we had a midterm exam. Any comments of anything on that?
Yeah, sure, time helped.
Extra time. But I did not give extra time, right?
It's,
Oh, 10 minutes, yeah. You mean the 10 minutes helped?
yeah,
Okay. You're not meaning the extra time to do the problems again.
no.
So it turned out long.
Yeah,
Actually,
Was yeah. Unusual. I usually don't make it this kind of exam, but I have you all can see your grades. I think you can also see the statistics if I'm not wrong, right? If you click on, I think you should have access to statistics. Statistics means it will tell you what others range of scores are. Doesn't tell you the exact. Yes, no? Okay. Or at least it's available, that's for your information. There's only two things I want to say. Problem 1, 2, 3 was very predictable. So I think most of you did good in that. So that is good. So I think that is the main thing we will be using. Problem 4 and 5 was sort of different, at least different from I have given hints on that before. I've even asked you as a extra problem. I think some of you even attempted it before, so that's good. But I would like to mention that problem 4, only Ryan got it right. And problem 5, only Pravina got it right. So that's only people. So that's good. So I thought, and that was good work, I think. That's, I thought I should mention that. And you have midterm, homework. The new homework has not been updated yet, uploaded it. I'll do that probably by afternoon. So I'm hoping that I can put in a new question. So by afternoon or later in the evening.
Yeah, the
Huh?
camera.
Other board. Oh, okay. Thank you. Okay. So we are now running homework. Which one?
Fine.
Fine. Very slow this semester. It will be 1 week from today, and how much is 1 week from today? Okay.
yeah,
Tuesday. And when is midterm 2? It's in April. From the date. Yes. And on this,
April 27th.
April. Is it Tuesday, Thursday?
Yes, Thursday.
Okay. Oh, yeah, there is a final exam also. Usually the final exam is not declared in the first week of classes. It is decided later in the third or fourth week of classes. So the final exam now for this course is out. The final exam date, not the exam. So it's on May 9, Thursday. And it's 2:45 to 4:45. Usually the university makes it a big deal that not to change the time of the exam. So if you're doing anything or if you're planning for anything, be careful. It will be hard to reschedule some final exam. So it's just university makes it. Which you guys all teach, right? So probably you say the same thing to your students also. Okay, so we have broadly covered two things in this course. One is we did functional derivative, which is the tool for discussing stationary action principle or any minimization problems in the form of integrals. That's very simply put in loose words. And we discuss stationary action principle, which is that of Newton's law. We basically discuss Newton's law in that context. Now that we have introduced the Lagrangian, you have seen that Lagrangian is kinetic energy plus or the minus difference between kinetic and potential energy. So most of the problems we did until now is we gave the equations of motion and we tried to write the Lagrangian for it, correct? So we were doing equations of motion. Newton's laws are given, then we write Lagrangian, and then we try to get back our equations just as a check. Then we try to do the Hamiltonian, and we even wrote the Schwinger's version of the Lagrangian for our case. Here now we say that the Lagrangian is always kinetic energy minus potential energy, and then try to do more problems. So let's say Lagrangian problems. So Lagrangian mechanics. So now we don't have Newton's law as a guide. So we are doing problems where we start with the Lagrangian from the scratch itself. So that will be called Lagrangian mechanics, like Newtonian mechanics. We start with Newton's equations of motion. So here we try to write the Lagrangian. And the main idea is that there is an action. Right? So that's the action, and it is dependent on the position. Right? So that's the action. Notice there is only one variable it depends on, and that is so this is a functional. So that's the action, and this is the position. If we don't specify, if we have not formed the trajectory yet, this is the possible positions. Like only after the minimization has been done, it becomes the position of the object. And general notice in particular that this does not have velocity. Right? Velocity is derivative of position, but it's not independent. Once I know position, velocity is known. That's what we are saying here in Lagrangian. In Hamiltonian, it's different. Momentum becomes an independent variable. So we do variation with both x and t. So that's strikingly different there. So action here will be t1, and in principle, I should also say, this also depends on T1 and T2. So it also depends on the end points, T1 and T2. This is equal. T1, T2, Tt, and the Lagrangian. This is the Lagrangian, and it depends on the position. Now I can write the time dependence. On here, I cannot write the time dependence because it's a dummy variable. After integration, it only depends on the limits. And it depends on the velocity. And it can depend on time itself. And while doing partial derivative problems, we have done these kind of problems where it depends on a function, then the derivative of the function and the variable itself. So for us, this should be straightforward. Only thing is that now there are three pieces to this. A vector means there are three components to that vector. We will not be varying T1 and T2, so this will be fixed. So if this is fixed, no dependence. We will, in this week or even next week, we will keep this fixed. T1 and T2 will not be varied. So there is no dependence. So there is only R dependence in there. But if we do change, then that dependence should be taken care of. And I'm starting to emphasize on that because in 2 weeks we will be changing that, and that will play a very important role in whatever we do. That's pretty much the calculus will be introduced in. Okay, so that's and this is the Lagrangian. And I will also say this is sometimes written as Vt. We will find it very convenient to write that as velocity, but that has this cautionary point I have to make, that it is not independent. The moment I write velocity, it is easy to say that obvious velocity is independent. On the left-hand side, there is no velocity. So I make variation only with x or r. And because of that, this changes. So velocity changes because I'm making the variation in R, right? So that's important. And the Lagrangian mechanics, some like Newtonian mechanics, we can introduce some concepts, and the Lagrangian will be equal to the kinetic energy minus the potential energy. And potential energy here, the kinetic energy, what does it depend on? We will say it just depends on the velocity square, maybe. So, or let me just write u first. So K, without having any coordinate system, we will always say is half mv squared for a single particle. And that will be, it is better to write it as v dotted with v. Okay, so remember velocity here is the derivative of position. So there are two derivatives sitting there, and it's a scalar. So it will be square quantity. For each particle, that is the case. So if there are three particles, then you have three such terms. And U similarly, interaction energy. So this will be dependent on. Typically, we talk about just R. But that's not necessary. It can depend on velocity also. We have done velocity dependent forces. Magnetic field is a classic velocity dependent forces. But most of the time you will see that it depends only on R. So it is significantly simpler, but you can have velocity dependence too. And T. And this is less common. If it is not velocity dependent, then this acts like a potential energy. So if it is velocity dependent, then we should be careful with interpreting it as a potential energy, because usually there is a term in the canonical momentum also. And the idea is you write the Lagrangian this way and use stationary action principle. So stationary action principle. Like stationary action principle is with respect to the position, so the variation in the action with respect to the variation in all possible positions, trajectory, all possible trajectories if you want, is equal to 0. Right, that's a vector equation, and this describes, so whatever equation comes here, that describes your mechanics, that's the idea.
Minimal action required to move a particle, minimal function.
No. Action required, that won't be the language, we will say, whenever the action is minimized, that particular trajectory that minimizes the action is what the nature will choose. Right, for example, if I drop an object, like I drop a pen from here, it usually goes straight. It could have gone this way, it could have gone up and got down, even though I'm throwing it from rest, we don't expect it to go down. Think of all trajectories possible. We are saying that the action is minimized. This is a number, right? You fill in all those trajectories that particular action, the number that you get out of it will be minimum for the one that is going straight, the one that nature picks.
One that chooses the minimal energy.
It's not energy, notice, this kinetic energy minus potential energy. So it is so what you're trying to have is you're trying to have an insight into what this quantity is. Nature is trying to minimize this. What is this physical quantity? No, it is not energy. Typically, we would say system does try to minimize energy most of the times. That is an interpretation you can have. Okay, what's the statement?
What is the units of Lagrangian?
It is the joules. Of course, it will be joules because it's potential energy and kinetic energy, right? Lagrangian is, if you're familiar with free energy in thermodynamics.
The Gibbs free energy?
Yeah, Gibbs free energy. Let's, there is a Helmholtz free energy, there is Gibbs free energy. There are few things we deal with. Now, if you notice, each one of them is constructed in a similar manner. Hamiltonian is what energy is going to be. So just for having an insight for what you guys want to connect with something, right? Hamiltonian is usually energy. When I say usually, when is it not? Whenever there is time dependence, Hamiltonian is not the energy because then it is not conserved and so on. But Hamiltonian is the energy whenever there is no time dependence. So for a closed system, let's say for the universe, we don't have any interaction with the surroundings. So then Hamiltonian is the energy. So for any closed system, which is basically a way of removing this time dependence, Hamiltonian is the energy. Okay.
Okay.
Now, that's equivalent to in thermodynamics, you have your, I think what you call that, heat minus, yeah, there also you will say the potential energy. It's the same, but then you define various quantities. You define Gibbs free energy, you can define Helmholtz free energy. This is equivalent to the Helmholtz free energy. Okay. So that's the way you can think of it if you are very comfortable with the thermodynamics and you have done this. But most of the time, what I notice is that you're not done enough thermodynamics, or we don't have enough insight in terms of thermodynamics either. So that's an answer that hopefully helps as far as insight goes, intuition.
The units is in terms of energy, but with the time variation, it's not energy, unless it's a closed system where time is. Nothing is changing, if nothing changes to your system for for some amount of time.
Correct. Yeah, because there is a good point you raised that typically I always say that the system tries to do whatever. And our system tries to minimize the energy. That's something that you can use all the time, right? But then now I'm saying that no, it is not the energy, it is kinetic energy minus the potential energy. So there is an additional piece there, right? So it is Hamiltonian minus P times V. So, and it is also important here, maybe I should say, the way this has been written, it is crucial that we are identifying the variables that we are varying very carefully. For example, when I build the Lagrangian out of the Hamiltonian, it is practically the energy itself, but I'm writing it as P dotted with V minus L. So that's so that I get the equations of motion correctly. So numerically, maybe the way to say it is, I'm not sure how correct I am here. Numerically, by numerically, I mean, I don't care for this R dependence. I just plug in the number, right? Once the minimal trajectory is calculated, I plug in the number for that integral, that will be the energy. Okay, check on that, my statement. Is that clear? So I'm saying the Lagrangian is having the information of energy itself. But
There is no position dependent.
if you calculate it for the minimal trajectory, if you calculate it, that will be the energy. But be careful. I mean, there is a few things I'm worried about here. Yeah, because by construction, it is negative. Right? So, but like especially the Hamiltonian that we built might be extra term, might not be crucial. So quiz, right? What is the interpretation, physical interpretation of the stationary action principle in terms of Lagrangian? Or what is the physical interpretation of the Lagrangian? Let's say, not the stationary action principle, you will see a lot of literature on it. But what is the physical interpretation associated with the Lagrangian? It is not the energy. Yeah, with that unsatisfactory answer, so let me proceed. Any comments or questions? Okay, so the best is, again, what we will be doing is that we will write the Lagrangian, write the action, or write the action Lagrangian and get the stationary action principle. So we don't rely on Newtonian mechanics anymore. We don't rely on F equal to ma anymore. And we try to do problems associated with that. So let's do an example. So example. Let's do a very simple example, which is almost the reverse of whatever we did earlier. Let's drop an object, right? We just drop an object in on the surface of Earth. As far as we are on the surface of Earth, we don't have to worry about the curvature of Earth. Is it necessary to worry about the curvature of Earth, by the way? If we are dropping,
No.
what if I drop it?
If you drop it from the International Space Station, then the curvature will.
What if I drop it something from aeroplane, from an aeroplane? Like I'm traveling in an aeroplane which is about 10 kilometers up.
I think at that time that goes to that doesn't go straight, that goes to
So,
the present
right there.
dimension.
Precision,
It's the curvature of matter.
the precision
Huh?
will be very
That's
small.
curvature of matter.
It will not matter, 10 kilometers. In an aeroplane, when we are dropping, so let us say if I drop a ball from here, it drops 1 meter, I measure the time it takes, correct? And let us say my watch has 2 significant digits, let's say 2 or 3 significant digit accuracy, and I'm doing a precise enough experiment, I measure the time, let's say 2 significant digits. Okay? I meure the time, and then I go to the airplane, do the same thing. Aeroplane is going steady. On the like 10 kilometers up, I drop the ball, measure the time again. Which one will be higher or lower?
The
To two
average-
significant digits.
Which one? The airplane would
first
would
part?
require
Huh?
higher
What is the
precision.
first part?
I drop a ball here in this room from 1 meter high and ask how much time does it take to reach the ground. I measure the time to two significant digits. My watch is not good enough to measure the third significant digit. Let us say I have a watch for various experimental reasons. I could measure only two significant, which is very big deal. By the way. Like most of the experiments that you guys teach, it's hard to get the second significant digit accurately. It's way off. So you need really good experimental skills for that. But let's say that you devised or designed an experiment which is really good. So two significant digits, you measure the time. Good. You take the whole setup in an aeroplane. Let's say you spend some money, a lot of a whole room there. You repeated the experiment 10 kilometers up in the air when the aeroplane is going steady, right? Like the motion is not really affecting it, it's just the drop that is mapping. And you do the experiment again. Which one will take a larger time or a smaller time? Or it will be the same.
So we talked about the gravitational acceleration on aeroplane previously. So
Uh-huh.
there's a one, I don't remember which significant digit, like if it goes to that, there's a change.
Correct,
Otherwise it
correct.
don't matter.
Yeah, so I have discussed this. So it turns out that if you, so I think we can tell this very quickly. I write it here, right? So I think the main idea is G. So this is GM over R square, right? Like, or let's say R square, right? That's the formula for G and that's the radius of Earth, let's say R, and you're usually somewhere here, little above it. Like I'm exaggerating that, but it is really small usually.
Yeah.
So this is nothing but, yes, GM R plus H square, right? So then the point is, what is R plus H? R is 6,000 to two significant digits, it's 6,400 kilometers. Like it's very hard to go into the third one. If you go to the third one, so these are the challenges that comes in. Then you have to say whether you're standing on the Everest or you're standing in a valley in Peru, like which are 8 kilometers or 10 kilometers. So then this is not the same. So if you are even to say that no, I'm going to do this experiment for three significant digits, then go and get the radius of Earth for three significant digits, and that's not easy, right? So this is a reasonable thing. So this is 6,400 kilometers. Let's write it in meters. So that's your meters, right? What this means is that these 5 zeros we don't have any idea about. Right? This is not really zero. We don't know what that is.
They're insignificant.
Yeah, so if you want, you will say that this is 6.4 into 10 raised to 6 meters, right? So this is only two digits in that sense. And now let's say the height h. If you're saying is, I said 10 kilometers, right? That's where the aeroplane goes. So 10 kilometers is somewhere here, right? So it is 0.01, right? 10 kilometers will be there. So I have to do this. Right, that's so if you write it in the same, so that's 10 raised to 6 meters. So if I add these two, so 6.4 plus 0.01 is equal to
6.41.
no, it's not 6.41, that's 6.4. Right, is that clear? Why? Because this is not significant. This digit is not significant. I don't know what that is. So whatever I add to 1, I cannot do this addition because this doesn't exist. This number is not available for me. So this is an error. Whatever I do here will be an error. If there is an error in this number, so whatever I do, there will be an error in this number. So I don't know this number. So there is an error. So you say it is 6.4. So the only time, so you can ask, how high should I go to get this going? So you would say that, when will this 4 get disturbed? Probably at least 100 kilometers, right? You have to go, or one can argue maybe 50 kilometers. Like when you're doing error, sometimes you will argue that maybe when it is 5, then it becomes 6.45, that can become 5. So those are all, so somewhere between 50 to 100 kilometers, then this becomes important. International Space Station is about 400, 300 to 400 kilometers, there it is important. Right, so then that changes to 2 digits. It really changes and it becomes 10% low. Yeah. Okay, so that's. Why did I bring this? Yeah, okay, that's because we were doing the example of uniform gravity. Uniform gravity is equivalent to saying that Earth is flat, right? When R is flat, you get the same GM over R. Or the uniform 9.8 meters per second square is obtained in that it is the density that matters in that case. So we again ask, what is the kinetic energy? So kinetic energy, so we are dropping a ball. So the ball is, so we are just dropping the ball. What is the what's the motion of an object which is having just g. Just to make this, now that we have 3 quantities, it is not necessary that a ball is dropped straight. You can also drop it at an angle. You can have a projectile motion, right? All that falls into that. So that's an example. So kinetic energy, we would say, is half mv square. And the potential energy now is equal to potential energy is mgh, right? Or you want the coordinates now. So it is mg, let's call it z, right, from the ground. But we would like to write everything in terms of r. So how would you write z in terms of the vector r? R cosine theta, but then I introduce a theta there. Right, something purely in terms of r and maybe, yeah, pretty much cosine theta, but maybe as vectors. I think what you're saying is that you can say this is mgr cosine theta, or maybe since we want r, the vector r dotted with z hat, maybe like r hat dotted with z hat. So that's the same idea that cosine theta is
Is the
coming.
word to like a dot, Z. Course.
Yeah.
the angle, Parallel. of the-
Yeah, this is also basis dependent in the sense that I have brought in z hat. But then I don't have to write it as z hat. Think of it as, let's say, n hat, where n hat is this. Or better, right? I think, yeah, let's not write it like this. Yeah, how about this? I think, isn't it correct that G dotted with R? Isn't this better? Like, then I'm not using any coordinate system. I'm not specifying whether I'm doing, or is that right? Is it?
Yeah.
Is there a negative sign?
Components of independent.
Is there a negative sign?
Yeah, there should, unless it's inside of G. But there should be a negative sign because the directions are opposite.
Like Z usually, like we are saying Z, I mean, in the problem we were doing, Z was up positive, right? And G was down, right? So it is cosine of 5, which is a negative sign, so I think that's the negative sign there.
Yeah, it should be
Right,
negative,
so that's negative sign. Yeah.
unless if you include
Yeah,
that sign.
we will know it immediately when we do the problem, we will get a wrong sign. I think it is, that's a. Is that clear? Okay, so nothing different, we just try to write it as vectors. So let me write this also, v dotted with p. Remember, v is derivative of position. Okay, so we have our action immediately then. So action, which is a functional of the possible trajectories, is equal to T1 to T2. I need to write the Lagrangian. Yeah, why not? I should write the Lagrangian first. Okay, write the Lagrangian first. So Lagrangian is equal to half m v dotted with v. Let's write it as r, like at this time. Let's not get lazy. D by dt of r as a function of time dotted with minus, minus and a minus becomes plus, so it is m g dotted with r. Right, that way I have all the places my r is available already there, and then I just started with the functional derivative, write the action. There is no variation in the endpoints, so it is just dependent on the possible trajectories. That's equal to integral dt t1 to t2 of m plus m g, which is a constant, g, m and g are constants. That's r t. With me? Variation of the action with respect to the possible trajectories. Says t prime is equal to t1 to t2 dt. There are two of them, they're identical. So it's the variation of r itself that comes in, so half goes away. So m times d r dt dotted with d by dt of variation of r with t over variation of r with respect to t prime. Plus mg dotted with variation of r with respect to t like that's the advantage we have had, that at this stage we can do this in a single step. Otherwise, most of the time, if we had not done the functional derivative clearly, then this is a complicated step. That's a delta function, so maybe still I'm doing it in a few steps. But probably helps. So this is m. At this point, I can replace, bring in short forms. So this is velocity v as a function of time dotted with d by dt of delta function of t minus t prime plus mg good point. So I think I should be careful here. I think we, yeah, I should at this stage bring this up. if we have defined, like I missed earlier, like we have defined this, correct? So x over x of t prime is equal to t minus t prime. Right? Now what we are doing is, there is a vector. Is the left hand side a vector? This quantity here, is this a vector? Is it a scalar or a vector?
The T prime, the R, vector R with associated T prime. Sounds good.
Let me. Think it's important. Let's. So think of it like this. This is a way of writing E by D R E prime acting on R of T, right? That's a vector. Like, that's something like a gradient, like something like a gradient vector, right? Is there a dot product in there?
No,
Yeah.
it's just a.
So now again, my question, yeah, so is this a scalar, vector, or something else?
It can be a vector.
It cannot be a vector because there are two quantities in it.
But it is gradient.
One over
Yeah,
scalar.
so what is gradient of R?
One over a scalar. One over R.
Now, think of this as a gradient, so it is a vector. This is a vector.
Is it a diagonal?
It's a dyadic, right? It's a tensor, it's an outer product. Okay, and what is this equal to in the outer product? What is this equal to?
3.
No,
1.
if it was a dot there, then that's 3. This cannot be 3 because it's a number. 3 is a number, right? So this is not a vector, this is not a scalar, this is a tensor, which often we will write it as a dyadic. Okay, this should be thought of as, for our purposes, this should be thought of as d by dx of x, like that's one component in rectangular coordinates. D by dx of y, d by dx of z, d by dy of x. And that's what, this is a short form for all this, but more than short form. When I went into this, I have chosen a coordinate system. Now I am in rectangular coordinate system. This doesn't care for which coordinate system I am in. I could be in spherical coordinate system, rectangle. This is a symbolic statement. Here, this is, it's helpful sometimes in rectangular coordinate, but if you have no intuition for this, this is what it is. Okay, Pradeep, Puja, right? So this might be new for you guys, like others have seen it in my classes earlier, so be aware of this, like that this is two vectors without a operation in between is a tensor. Often in other textbooks and other courses, you will write a not cross product. This is not a cross product. Cross product of two vectors gives you a vector. Right? This is not a vector, it's a tensor in part. This is an outer product. Like often we see it in quantum mechanics a lot. So this is the same outer product, but I don't write that at all. So this is following Schwinger, like we just don't write it. It's understood that when there are two vectors, there is no operation in between. We will say that's a tensor. Okay, so coming here, these are two vectors, Right? No operation, so it will be a dyadic, and in this case, it will be exactly one. That's our definition, if you want. So here, this is a delta function, but with an additional feature that there is a one here. Okay, that's important because now I need a dot, it has to dot with something, right? Suddenly like especially here, this was a vector dotted with something. If I just write delta function, what is that equal to, right? You cannot dot it with a scalar, right? So I need some quantity to dot it with. So that's your one. And just for just as very 1 minute crash course on dyadics, if you have a vector A dotted with one, right? This will be equal to, so one, so it will be just one itself. It helps to think of these two vectors as two vectors, the two arrows as two vectors. That's one vector, that's another vector. Dyadic is built out of two vectors. So it is dotting with the vector on the left. So one of the index is free, so I have to get a vector back. In index notation, you will see, if you're familiar with index notation, you would say this is ij will be aj, right? If you're familiar with index notation, but probably you guys have not even seen index notation, or you're not very free with index notation. So this is a notation that we will use. Any comments or question on that? Okay, so the main thing I have added on is that I should have said this before when we introduced the vector quantity, that's one there. So the same thing works here. So this is one in here. T times T prime, and now this is one. Pretty much the same as earlier, except that now you introduced a one in there, and one is very straightforward for our purposes as a user. Without worrying about the details, that it acts on any vector to give me back the vector itself. One is exactly like one, it's like a matrix, right? Okay, good. Now I can do the integral. Remember, derivative of a delta function gives you negative of the quantity that is there in front of it, with the derivative acting on the other side. And here there is just a delta function, it just evaluates that quantity. So I'll go to the. Actually, I'll go up. Oh, I can go here, right? So move the camera. So the variation of the action with respect to all possible trajectories is equal to evaluate the delta function. So it is minus derivative of mass times velocity. Velocity, remember, is derivative of r, right? So maybe write it like that. And this time it will be T prime, I guess, right? Evaluated at T prime. Is that right? T prime. No.
I think it's 2T, I guess.
Is that the?
Goes to, okay, yeah, I'm just talking about the another T. Because we're not taking the 2T.
Yeah, here, this one, yeah, that was my bad. Yeah. Okay, so this is derivative acting on the other side, negative sign comes because delta function, it's a derivative of the delta function plus mg. Okay, yeah, and there was an mg dotted with one and velocity dotted with one, but one just acted with anything else is just one itself. Clear? Next is the action principle. So you say this is 0. This is equal to 0. So this is the stationary action principle. This is what replaces Newton's law if you want stationary action principle. You're saying that the action for the trajectory that the object will take is stationary. Stationary means it is an extremum, maximum, or minimum. Set this to 0 and we immediately see that it is d by dt of mass times velocity, let's say now, is equal to mg. And that's, I think, that equation. No sign problem there, I guess. Right.
Yeah.
Okay, so that's a simple example. I might have said earlier that whenever forces are involved where we cannot write an expression for the force, like it's not a conservative force, then Lagrangian is not very useful. For example, the normal force or the force of tension. Can you write an expression for the force of tension?
Just no.
Typically, from a fundamental point of view, we never write an expression for the force of tension. Only thing we do is that using Newton's law, we say that the force of tension is equal to mg cosine theta, or we'll relate it to another force, but
Use another fundamental force to.
exactly, we relate it to another force using Newton's law, but tension itself, we never associate something with. So that would mean that, oh, whenever there is a force of tension, I cannot use Lagrangian, but it turns out that if we ask, what is the force of tension doing? Let's think of an example of a pendulum. Yeah, so let's do the next example as a pendulum.
Think of what is the action doing.
Yeah, so first let's think of the pendulum like the classical Newton's way. So that's your pendulum, that is a length L for the pendulum, like that is the only thing involved, and there is a mass M, right? It is hanging off the and what's the equation of motion for this? So what are the forces, like you would say, now we are doing Newton's mechanics, not Lagrangian. So you would say Newton tells us that mass, this mass, times the acceleration of this mass, right, is equal to the forces acting on this. What are the forces acting on this? That is mg acting down.
So as the force.
Force holding the wall up, and that is the
would be
force
like
of
normal force.
tension, right? You say there's a rope, that is, this is a rope, let's say. Maybe it is not clear, it could have been a rod also, like, let's say this is just a string that we use to stretch it, so that's your force of tension, right? And what are the other forces acting on this? Mg, the second force acting on is T, right? Let's say there is no air resistance, right? And there is no drag, so what are the other forces acting on us? That is it, yeah, that is it. There is no other force acting on it, so there's only two forces acting on this mass. Agreed? Lakshmi, you don't seem satisfied.
Shouldn't there be negativity?
When okay, the notation I'm having is that when I say there is a vector sign on it, it has everything in it. When I come to the actual representation of it, let's say x, y, z, or any coordinate system I use, then I have to worry about negative or positive. Currently, these are two forces. I'm only identifying the forces, some vectorial forces. So maybe, does that help? Yeah. Okay. So then we have to ask what is the like as Dilakshi was thinking, like we need to have the components of this, correct? So And tell it again.
We need an angle.
Yeah, usually it comes out convenient to write this down. We have to use a coordinate system. That's the point, that we have to use some coordinate system. Typically, a coordinate system that is useful is a radial and tangential component. So let's say this is radial. And tangential could be this way. That's your phi hat. That's your radial direction and phi hat. And why is that? I mean, you might have seen this in Newtonian mechanics also. Once, this is the first step in Newtonian mechanics, then always use a coordinate system or your axis such that one of the axes is in the direction of acceleration. It's just a trick, it helps. Okay? If you don't, nothing will happen. It's just you'll have to do some 2-3 extra steps. Right, but algebraically everything will work out. But if you choose it, then it helps. What's the direction of acceleration in this problem?
Going to the left.
It is angle, then we sin theta.
So is it in the
5 degrees.
is it in the phi direction or is it in the radial direction?
5 degrees.
It could be
Oh,
in
it is
the
5 degrees.
both directions.
Don't say it's in the both direction.
I mean, there's still the phi direction because it's still kind of moving in a circle. It's still changing. But no, the length will be constant, so it's just.
It's just the angle.
So it is in the tangent direction?
Yeah.
Can you go in a circle without acceleration? Is the question clear? Let us say you're driving on a straight line. And it's frictionless. And you try to change lane, that means you're trying to take a turn, let us say, right? So you're going this way. It's extremely icy road and you have to go that way. Right, that's a circle. Correct? So how will you turn? It's an extremely icy road. You'll have to accelerate. Huh? Right. So give me a maneuver, those who have driven. How many of you drive? How many of you drive, Pradeep? It's only two. It's a good number. So okay, imagine you drive. So that's very hard example to give. Oh, walking, let's say. Okay, you're walking. Okay, walking is like it's like skating. Have you been on the skating ring ever?
Yeah.
How many of you have stood on ice? Stood on ice? Like surely
Yeah.
you're from a mountain probably, right?
No,
You're on the valley?
Yeah,
Yeah.
I'm from the valley, but last year I went to the West Coast, that's okay.
You understand a driveway? Driveway is a very small region of like you're coming down the stairs, let us say. You all have apartments, you're coming down the 3 steps, and let's say there is a small slope, and it happens to be a perfectly icy day. Okay, perfectly icy. By perfectly icy means we don't even have a little bit of, usually we have some friction, right? Because there is snow on top of ice and there is a small gradient right in front. Okay. How will you avoid slipping?
Increase the we have to just increase the speed.
Okay, so that's your slope. My question is, this is your driveway, that's your angle theta, right? You're standing now. Right, that's your mass, that's you, right? This is you. And this is frictionless. Right, my question is, you want to avoid slipping, that means you don't want to slip. Okay, how will you avoid it? In this case, how will you avoid not falling?
Lean back.
So this is acceleration, right? How will you avoid acceleration?
Guess I'm just kind of thinking, if it is perfectly circular, you're going to slide.
Yeah, that's the next question I'm going to come up with, but this is simpler, right? And make it small, like usually you have a lot of flexibility in your hands and you can hold on to something. But make it ideal scenario where you don't have any help, right? You cannot hold on to something.
You have to be very slow.
There is no way, you cannot avoid sliding.
You're going to slide.
That's thrust and fluids. If you're here, you will fall. There is no way you can save yourself.
Yeah, yeah.
Right, this will accelerate. Right, if I'm saying frictionless. I usually experience defines us because we usually have a little bit of friction, you can hold on to things. But if you're here, if you're on a driveway, if it's big enough, you are going to fall. So wear a better dress so that at least you can save your fall, that's the best you can. But if you trust your equations, you will fall, right?
You have to sit and
You
then
just
you
gotta
hide
work
it
with
back.
Now let's stretch that here. Okay, now I'm going straight, frictionless. Okay, I have to go here. How will I turn? How should I maneuver my turn? Like think of your car, so it's harder for those who are not driving. The idea is that you have to turn, right? How will you turn so that you don't create an accident, like there is another car here, there's another car here, so you want to make sure that you're on your lane.
Slow down.
You can't
We
slow
have to
down.
slow
You
down.
just gotta
How do you slow down?
keep going,
How do you brake?
just turning this.
In the,
During the friction to the.
Friction, right? Icy road, I said.
it's not a friction.
There is no friction.
Use the motion of your initial motion to turn.
Is that clear the challenge? We don't have friction. Okay, so if you don't have friction, how do you turn? So Ryan is saying just use your motion to bend.
Your brakes will not work.
Hmm?
If you
Yes.
break, then
I think that's correct.
Maybe you can't.
We can't. Whatever you do, if it's an icy road, you cannot take a turn. That's why if you're on an icy road, you will see a lot of accidents because you're trying to change your lane. You think you can. We are used to our experience that, oh, I can manage this, just turn. But there is no friction, so you're trying to change lane, so you want to come here or here in this case, right? But your car will bend because you turned your wheels, but it will go straight. There's nothing you can do about it.
it happened with me.
Sorry. Be careful. Use your physics. Right, so the main idea is that Newton's first law tells that if you have a velocity, unless there is a force, you cannot change its velocity. Right, there is no availability of the force, the friction is not available. So there is no force, so you cannot accelerate. If you cannot accelerate, you cannot change your velocity direction. Right? Velocity direction has to be changed for that. And so you cannot go in a circle without acceleration. You cannot accelerate without a force. Right? So it is impossible. But with a small catch, the catch is that you have these designs, banking of roads,
Yeah, angle of bending.
there you can.
You can turn.
You
without
can
actually
turn on a
turning.
banked road. How does that help?
That's really fun.
No, how does that work? How does it work?
The thing we have centrifugal. So
How are you able to turn on a banked road?
It,
Using the
no,
Why
I
doesn't
did
it
this
slip?
before.
even angle,
Yeah,
with like,
On the
the component of. Weight of the car.
so the quiz question is, which force on a banked road? Or how are you able to turn on a banked road? What's the big deal? On a frictionless banked road, will you slide? Can you take a turn on a frictionless banked road? Is that clear? Is it even possible?
One more
On a frictionless
bank.
bank road, on a frictionless road, I argued that you cannot turn. Can you turn on a frictionless banked road? Okay, and address that. Is it even possible? Okay, is the question clear? Okay. And then we'll come back. And then the question is, what is the acceleration in here? That was the whole point, is that,
Yeah,
so this is going in a circle. If something is going in a circle, there has to be a radial acceleration. Yes, otherwise you cannot go in a circle. That's the point. So that point that it is only tangential, that's not a true statement. Otherwise it cannot go.
that's why it's not. That's also why it's not a true force.
It's an acceleration, it's an effect. The cause is you need a force to do that. But eventually it is the acceleration that is the effect. Who is giving you that acceleration? It is T and a component of mg. But it has to be in such a way that there must be an acceleration. If there is no force, you cannot accelerate, you cannot go in a circle. Earth is going around the sun, same idea. Force is radial. Can you go in a circle without a radial force, but only in the tangential direction? Let's think of a spacecraft. There's no gravity, imagine, like think of it going in a circle. But let's say you design a spacecraft which is going tangentially, and always the force is in that case the thrust, right? So it is tangential. There is no gravity, there is no sun at the center. Will you go in a circle? You won't go in a circle. You need a force in the radial direction. If you want to go in a circle, you want to push that side. When you turn your car, friction is acting towards the right or your left. Right? When you pull something on a circle, you're pulling perpendicular to the motion. Velocity and acceleration are perpendicular in circular motion.
Trigonometry is SOHCAHTOA or cosine to figure out the angle, you have to know the tangential components and so adjacent over hypotenuse, x equals the, if x is the adjacent, x equals the hypotenuse times the cosine angle, so we're still in tangential.
I lost the.
Tangential and radial direction.
I lost track of your thoughts.
I was just kind of thinking of like a triangle.
You're probably thinking a lot.
Yeah, we
Good.
usually do.
Good. Okay, so we'll do the example of pendulum next time and do few examples, basically do double pendulum and make it complicated, but the idea is do some simple examples. I won't try to complicate the examples too much, try to get the essence of the Lagrangian mechanics. That's the idea, not to make it too complicated. But one can do 4-parameter problems and so on. It is how you do use. Okay, I'll stop here. I got late. Keeping a good